So far we have merely been describing how points in a system actually move. Now let's look at why they move, and that will be using the concept of forces. Newton's first law: a body will remain at rest or at constant velocity unless acted upon by an external force. This is Newton's first famous law. In practice, it deals with inertial frame of references, and we define an inertial frame of reference as one in which the acceleration is zero. It's a set of coordinates x, y, and z that are just coasting along at constant speed or not moving. Newton's second law: the net force acting on an object is equal to the rate of change of momentum. Momentum is defined as the product of the mass of an object multiplied by its velocity. Just a little note that this is just classical momentum. Either in this video or another, I'm going to go into relativistic ones, but for all of these we are dealing with velocities well below the speed of light. Once we take our little triangle to get smaller and smaller and smaller, we involve calculus, and the net force is equal to the time derivative of the momentum. Well, if the mass is equal to a constant, then the net force is equal to m dv by dt, where dv by dt is, of course, just the acceleration. Newton's third law: if two objects interact, they exert equal and opposite forces on one another. So, for instance, these could be about to collide, and after they collide, object A will experience a force due to object B this way, and object B will experience due to force due to object A going this way. It could also be something like electrostatic repulsion, for instance, and Fa will be equal to minus Fb. There's one more quantity, really important one, that we need to define, and that is impulse. So because of Newton's second law, F is dp by dt. If we were to bring the dt on one side, we're going to be left with F dt is equal to dp. Now we can integrate both sides with respect to time. On the left hand side, we're going to get this quantity, the integral of F dt from t1 to t2, and this quantity is known as the impulse. Maybe I should write it over here, that this f by dt often is given the symbol j, but this can vary a little bit from country to country, and that is impulse. Okay, well, if we were to integrate all the tiny changes of momentum from one time frame to the other, or from one time to the other, we're going to get the overall change of momentum. And we have yet another really important rule in classical mechanics, that F dt is equal to the change of momentum. So, in other words, if we have a graph of force against time, the area underneath, sometimes we can just even approximate it with a nice regular shape rather than having to do a tricky integral, will be equal to the change of momentum. We can even say that this is equal to m, final velocity take away initial velocity. Moving on to the center of mass. We can define the center of mass as a point with some x, y, and z coordinates where all the mass appears to be. How do we get that? Imagine that we have a whole bunch of particles right over here. Each of them are going to have their own displacement vector. Well, what we can do is we can take one of those masses, multiply it by its displacement vector, which is going to have its x, its y, and its z component. Then we're going to add up the second particle, m2, I don't know, we can call this one m2, and that's going to have its own displacement vector, distance x away from the origin, distance y, and distance z away from the origin. To find the coordinate of the center of mass, all that we need to do is, well, divide this by the total mass. So x coordinate of the center of mass will be equal to m1 x1 plus m2 x2 plus dot 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 divided by the total mass, which is going to be given by m1 plus m2 plus etc. This is repeated in all three dimensions, and finally we have an equation for the center of mass. It will have a displacement vector r center of mass, which will be given by one of those masses multiplied by its displacement vector plus another one multiplied by its own displacement vector, and it's a summation sign. Please note that if you have a continuous mass distribution, those sums over here will turn into an integral, as we're about to see. In practice though, for symmetrical figures, we can just use principles of symmetry. So for instance, the center of mass of a circle or a sphere will be right in the center, assuming continuous mass density and uniform distribution. Same here with a uniform rod, for instance, the center of mass should be dead in the center. Or should it? Well, let's have a look at a little problem. So show that the center of mass of a uniform rod of length L and mass m is right in the middle. Typically, we would solve these problems with integration. As long as it's a continuous mass distribution, we can totally assume this. The way we tackle these problems is by looking at a small element dm that will also have a little width, which is going to be dx. Because the mass is uniform, we know that its mass dm, so this thing also has a mass which is dm over m. So that tiny mass over the total mass should be equal to its width dx divided by the total length, which is going to be L. And now we're ready to do an integral for the center of mass. So the center of mass was equal to the sum of each of those masses multiplied by its displacement vector. Well, this sum will turn to an integral, so we're going to have the integral from length 0 to L of the mass dm. We're summing all of those individual pieces along the length of the rod multiplied by the displacement vector of each dm. This here should really say dm. We're going to divide this by the total mass, which is just given to be m in total. Please note that if we don't know the total mass, the denominator will also be an integral over the length, but in this case, well, we know that the total mass is m. Okay, now we're going to need some common integration variable so that we can actually perform this integral. So I'm going to say that just rearranging for dm, shall I just do that over here, that will just be equal to m times dx, and then divide that by L. Now, if this here is dm, this here can get essentially placed across here. Now, its displacement vector in one dimension, assuming that the horizontal axis is our x coordinate, I've just called that x. I could have used the integration variable r, but because it's horizontal, it kind of makes sense to use x. And look at this. Now we can do some cancellations. So first of all, shall I just do the integral from scratch just to make this absolutely clear? The m's are going to cancel because those are just a constant essentially, so we can just do this. Let me get a slightly better pen. And then what we're going to get is 1 over L, and then simply the integral from 0 to L of x dx. Okay, well, this here will just be equal to 1 over L. The integral of x dx is just going to be x squared over 2, and that's just evaluated between 0 and L. So the 0, 1 will just get cancelled out, so what we get is 1 over L multiplied by L squared over 2, and this just gives me L over 2. So the coordinate of the center of mass of a uniform rod is indeed right in the middle. Now we're going to have a look at some basics, but then we're going to be applying them to some of the hardest problems ever in the International Physics Olympiad. So in terms of whenever the forces are balanced, we're really talking about statics. So we can balance out forces as vectors, pretty basic. So if we have -5 newtons and +5 newtons, the total net force will be equal to 0. We can also balance them out by components. So for instance, I can have the tension across here, then a force pulling something the other way. I can probably demonstrate this actually with my ID. So there's a tension component, and that tension component is balancing out both the force with which I'm pulling this, but also the weight, because this thing here is staying stationary. The force provided by the ground is known as the normal force, which is equal to mg whenever this thing is laying on a flat surface. Normal means perpendicular, so this force here is always at 90 degrees to the actual surface. If we were to put something on a slope, then the normal force would just be equal to mg cos theta. Why is that? Because the weight mg can be resolved into two components. So one which is parallel. The parallel one, basically this angle theta can be proven to be this angle theta. So the parallel one is the opposite, mg sine theta, and the perpendicular component, this actually is going to be equal to the normal force. That's just going to be mg cosine of theta, which is just this component of the weight, with that vector being equal to that vector. If this thing is going to be on the slope and if it's not moving, then we're going to need to have a frictional force. We can have kinetic friction, which is the force that appears once something starts to get moving, and this is given by the coefficient of friction multiplied by the amount of normal force. We can also have static friction. So if we were to start to push something which is not initially moving, there's a certain minimal force that's required to overcome the static friction, and that can also be calculated. Usually experiments show that this is proportional to the normal reaction force. For an object to be completely in equilibrium though, we also need to balance out the torques. Now this can get a little bit confusing. So in the UK we call the moment what in many other places is known as torque. So I'm going to use them interchangeably. I mean the amount of force multiplied by the perpendicular distance from the line of action of the force to the actual pivot. We can balance out the clockwise moments and the anti-clockwise moments for complete equilibrium to occur. All of these are typically studied within high school courses. However, let's apply them to some really tricky problems from the International Physics Olympiad. We have a heavy vehicle which is going down a slope, and this can be modeled by a front cylinder, they call that M3, and a rear cylinder, they've called that with a mass M2. They're connected to a frame across here, and they've given us some distances. So the very first thing is that we need to draw all the forces that act on the body, the front cylinder, and the rear one. Write down the equations of motion for each part. This has to be one of the trickiest force body diagrams ever, but let's get started. So the first thing is the force that act on the body. By that I presume they mean this horizontal frame. So the first thing I'm going to do is I'm just going to redraw the frame so I can focus on these forces without having a diagram that is a little bit too cluttered. Okay, so this here is our frame. Now, what sort of forces are acting on it? The obvious one is going to be the weight that is going to be acting at the center of mass. Let's say that this is around here and or about here, and we're going to say that this here is mg. Now in Olympiad problems typically we have to consider torques as well, which are really important, but the key bit is what is this frame actually attached to? Well, the front, it's attached to the front cylinder, kind of acts like the front wheel, and in the rear it's attached to the rear cylinder. Okay, so we're going to try and draw this as well, because there's going to be a frictional force from the attachment point, but also a component of the normal force. Okay, so there's going to be a force from the front cylinder, which is going to be a normal force. So we can just draw it this way, and this force will be upwards. Now this is preventing this frame from hurtling towards the center of the Earth. The mass scheme does something really clever by saying essentially that the force that acts on the frame from the front cylinder 1 is just called N, and it's acting on object 1 from object 3. It will also have a frictional force. The frictional force will be opposing the motion down the ramp. So we're going to have another vector which is going to be acting along here. So this vector here of a frictional force will just be acting on 1 from object 3. I think the mass scheme definitely assumes that object 3 here is just the front cylinder. Now, essentially the same thing will be happening at the attachment point for the rear cylinder. And we can draw our second normal force along here, assuming that this here is the attachment point for the rear cylinder. Now this normal force, should just make it a tiny bit smaller, will also, or this attachment point will also be providing another frictional force, which will also be opposite to the direction of travel. So I'm going to say that the frictional force is acting on object 1 from object 2 being the rear cylinder, and the same with the normal force. It is acting upwards on the horizontal frame from onto object 1 from object 2. We can also resolve the weight vector mg. So just move the mg sign over here, and this is going to be very, very useful. If the angle of the inclined plane is E dot, I'm just going to call it theta for now. I'm just so used to writing things as theta. Then this angle here will just be equal to mg sine theta, this component, excuse me, and this one here will be mg cos theta, where mg is just the resultant vector, which is just down here. Okay, now this diagram now is pretty accurate. We can now start resolving in both the perpendicular and the parallel direction. So I'm just going to start off with the direction which is parallel to the slope. So we can say that the parallel component of the weight, which is mg sine of the angle, and then minus the two frictional components, what is that, minus F12, then take away F13, will be equal to the total mass multiplied by the acceleration, the parallel acceleration. Okay, so this thing has a mass of m1, so I'm just going to call that m1, and to give some subscripts along here. So then, perpendicular to the slope, we are going to look at those forces here. So, oops, we need an upwards arrow here. We have mg cos theta, which is acting straight down. So we can say that mg cos theta, and then we can take away in the opposite direction. That will be N12, that's one normal reaction. And then from the other one is going to be N13. Now there's no movement in the perpendicular direction. This thing is moving purely in the parallel direction. So the sum of all forces should be 0. We can directly say that mg cos theta is going to equal to n12 plus n13. We've balanced out the forces, but let's also consider the torques, or moments as we also call them in the UK. Okay, so I'm going to take moments around the center of mass, and if this distance here is 2L, that means this here is going to be L, this here is going to be L. So let's balance out the torques. So I'm going to have N12 times this perpendicular distance, which is L, plus the other one, which is N13, also multiplied by L. Oops, this one here is going to be in the opposite direction, so let's take that away. And then what we need to consider is the torques from the frictional forces, because they're also going to have a perpendicular distance, and the mass scheme gives that distance here as h1, I believe. Okay, so the next frictional force that can create a torque is going to be F12. So we can say plus F12, then the height h. Okay, I think it was called h1. Why is that? Because if this height here is h, this is actually the perpendicular distance from the pivot to the line of action of the force. Those two should actually be in the same direction, so this here will be plus F1, those should be equal to 0. In Physics Olympiad, we can also get questions which are based on Hooke's law for elastic materials, so the force being proportional to the extension delta L, or the amount of compression. We can really just call that sort of change in length. Okay. Now, we need to define tensile stress, which is given by the force, the amount of force which is perpendicular to an area divided by the area, and then the tensile strain, which is the changing length divided by the original length. So what is a tensile force to begin with? It's simply a force which is stretching an object, and it's to be contrasted with something like a compressive force, which is, well, trying to compress it. Young's modulus is simply defined as tensile stress over tensile strain, and if we were to play around with these equations, we're going to get the force divided by the area, and then divided by the strain means multiplying by L0 divided by delta L. On to rotational dynamics next. Newton's laws can also be expressed in rotational form. They're incredibly similar to the translational laws, which each quantity having its own equivalent. Let me show you. So Newton's first law, a body will remain in a state of rest or constant angular velocity unless acted upon by an external torque. So in this case, we've just removed or added angular to the velocity, and we've replaced the force with a net torque. What is actually torque? Well, we can think of it as the product of the force multiplied by the perpendicular distance between the pivot and the line of action of the force. Mathematically, this is equal to the cross product of the displacement vector r towards the pivot multiplied by the vector of the force. The units of torque will therefore be Newton meters. Newton's second law can also be expressed in rotational force with the torque equal to the moment of inertia multiplied by the angular acceleration. We're going to delve really deep into what the moment of inertia is. For now, we can think of it as sort of the equivalent of mass in the rotational world, but let me just quickly introduce Newton's third law, which is far more intuitive, and that is that if we have a couple of objects interacting in the rotational world, then they will exert equal but opposite torques on one another in pretty much exactly the same fashion as Newton's third law. Now, let's explore this deeply because this is an excellent exercise in integration that comes up a lot in Physics Olympiads. Let's explore this quantity, the moment of inertia, even further. So let's consider a disk, and we're going to spin this disk with a constant angular speed omega, and we'll be spinning it around this axis of rotation, basically around its center. Okay, now let's consider a whole bunch of particles. Let's say that this one here has a mass m1 and a certain distance towards the center. Let's call it r1. These should all be straight lines, by the way. We can also have particle m2, which has a distance r2 from the center. Let's take one more. Let's call this one m3, and this one here will have its own distance from the center. You can call it r3. Now, the total kinetic energy of those particles, and we'll do a sum over all the particles, will be equal to a half, let's say m1. If particle m1, let's say that it's moving with a speed v1 squared, plus a half m2, let's say this particle here, it's a little bit more further out, it'll be moving a little bit faster linearly, v2 squared plus a half m3, and then this one here will have its own speed, call that v3 squared. Okay, now what we're going to apply is the fact that v is equal to omega r, and all of the particles here are going to have the same angular speed. If they don't have the same angular speed, then the disk will essentially disintegrate. But okay, so the kinetic energy, should we just say add a little dot 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 plus all the other particles, but the total kinetic energy will be equal to a half m1. Now v1 squared will be given by omega r1 squared plus a half m2. v2 will be having an angular speed omega times r2 squared plus a half m3. v3 is going to be omega r3 squared. You guys get the idea. Okay, now looking at this equation, we can get a factor of a half. Then we have omega squared that we can take out. And then what are we going to be left with? We're going to have m1 r1 squared plus m2 r2 squared plus m3 r3 squared, summed up for all of them. We can write this as a sum half omega squared. Shall we just say this is equal to mi ri squared, from I is equal to 1 for the first particle up to n particles that the system consists of. Okay, now look at this. This quantity here is actually the equivalent of mass in the rotational world, and we can call this the moment of inertia. Let's add a little square here, because if we look at this, the total kinetic energy will then be equal to a half I omega squared, really similar to a half mv squared in the translational world. How do we actually find the moment of inertia in practice? So it's typically about solving this integral. I is r squared times the sum of all of these masses. If we have continuous mass density distribution, we've essentially replaced the summation sign from before with an integral sign. Typically, we have to find a way to express the particle dm, or the variable dm, in terms of the variable r and perform an integration with respect to this variable. Let me show you. We have a rod, a uniform mass density rod that is spinning along this axis. So essentially it is doing something like this. What is its moment of inertia? Well, if it's spinning around this axis, let's say that we take a small element with a mass dm, thickness dx, that is x away from the axis of rotation. We can write down our integral as I is equal to the sum of all those dm's multiplied by the distance towards the axis, which squared, which is just x squared. The boundaries of this integral is just going to be from 0 to L, assuming that the length of the rod is L. Okay. Now we need to find a way to express dm in terms of the variable x. X in this case is kind of like r in here. I've just called it x because this essentially is a one-dimensional problem. Well, because it's uniform, dm over m, the mass of this little thing over the total mass will be equal to its width, dx, over the total length. We can rearrange for dm and we get that this is equal to m over L multiplied by dx. Then we can put this directly into our integral and we get the integral from 0 to L of dm, which is m over L dx, which I've put here, multiplied by x squared. And now we've got a pretty simple integral to perform. A lot of the times in Physics Olympiads, the integrals are not super tricky because people want to test out not so much integration skills, but applying the physics skills. Not always though, some of them can be time consuming. Okay, so we get the integral of x cubed over 3, which evaluated between 0 and L gives me L cubed over 3. Then we had a multiple of m over L. Okay, well, the length here is going to cancel, so what we're left with is ml squared divided by 3. Please note that this is the moment of inertia with respect to only one of its axes, and there's infinitely many moments of inertia if we decide to spin the rod in a different way. Moving on to the next example, and that is the example of a uniform ring of mass m. This is a nice and simple example. So we've got a uniform mass density ring, so all of those elements dm are going to have exactly the same distance towards the axis of rotation. We're assuming that we're spinning the ring around this central axis, so we're spinning it sort of this way. Okay. Well, our integral will just be then the sum of all of the masses dm multiplied by their distance, which is going to be the radius r squared. In this case, all of the points are going to have exactly the same distance. If you've not seen this symbol before, it just means that we're integrating in a closed loop and we'll end up where we started. Typically, you see this appear in circles and spheres and problems connected with this type of symmetry. Well, because r is just a constant, we can take r squared outside of the integral sign. So we just have the integral of over dm, and that's going to be with boundaries of integration. I've not really written them, but let's say from 0 to m. That's just going to give me mr squared. And this is a nice and simple problem. We can also have the problem of a uniform disk, just a tiny bit more complicated. How do we deal with this type of problem? Typically we consider slices. So we're going to take this slice here, and then we're going to integrate the slice from 0 to the total radius. By the way, this is precisely the same way that you would find the moment of inertia of a cylinder. This essentially is the same proof. In fact, I've just assumed that this thing even has a small thickness or small height dh. So think of it as a small cylinder. It's exactly the same way, same moment of inertia. This proof, by the way, is for an axis that runs straight through the center. So the moment of inertia of a uniform disk straight through the center. I is equal to r squared dm. This is the integral that we're going to be seeing a lot in moments of inertia. And this here will be equal to, well, we need to figure out what dm is in terms of the other variables. So a good way to go about this is to say that dm is density times volume. Excuse my writing here. I know there's a lot of symbols and things, but dm is density times volume. Okay, now what is the volume of this thing here? Maybe I'll just write it here. It's going to be 2 pi r, where r is just the distance towards the center. Then let's say that this thing has a thickness dr, and then I'm also going to multiply by one more dimension. Why not? We live in a three-dimensional world, so this essentially is a small cylinder. I'm going to call it dh, and dh is kind of like the thickness which is into the board, if that makes sense. All of this stuff here is going to be a constant, so rho 2 pi dh, so we can take that outside of the integral sign. So what we actually have left in here is, well, 2 pi r, sorry, just r, multiplied by r squared, which was originally in the integral, giving me r cubed, which I'm going to integrate from 0 to r with respect to r. And once again, it boils down to a relatively simple integral. Okay, well, this here is just going to give me rho 2 pi dh. The integral of this is going to be from 0 to r. Evaluated will be r to the power 4 divided by 2. But have a look at this. We can express r to the power 4 as r squared multiplied times r squared. And that's going to give me pi r squared multiplied by dh multiplied by the density. Well, this actually is mass over the mass times, the volume of the cylinder, which I've written over here. And if we're to plug that in, we're going to get that the moment of inertia of this cylinder is equal to mr squared over 2. There are infinitely many problems that can appear with the moment of inertia. Typically, you would find in the entry-level Olympiads perhaps a derivation similar to this one. In the international ones and also in the national competitions, which are pretty similar to the international competitions, you typically going to find combinations. So let's have a look at a problem which is a combination of a few different moments of inertia from the International Physics Olympiad. So we need to calculate the moment of inertia of one of the cylinders from the previous question. So where we looked at the free body diagram of this vehicle here, the front or rear cylinders actually consist of this. It's a model of a wheel with 8 spokes with a total mass of 0.2 m. The inner radius is Ri is 0.8 r naught. We can directly apply the moments of inertia that we've learned in the previous question. If in doubt, we can always rederive it in a competition situation, but probably try to remember some of the basic ones. So for instance, for the rods that are for the spokes that are moving along here, we can say that their moment of inertia is essentially just what we derive for the moment of inertia of a rod that is being spun around one of its ends. In this case, this is the center of the wheel. And the moment of inertia that we derived was a third m, and then the length of the rod squared. Okay, so there are going to be 8 of those. So this is essentially for 8 rods like that, and we're going to have their mass, which is 0.2. For one of them, this is going to be just 0.2 over 8. Of course, we could have just written this as 0.2. However, I just want to highlight that there are 8 individual rods. Okay, so the mass is m. We also had a factor of 3. And then the length is going to be 0.8 r naught, all of this squared. Okay, so what we're going to get is 0.0427 m r naught squared. And that's the moment of inertia just of the 8 spokes. The second part will be the moment of inertia of the cylindrical shell, which can be derived using the exact integration process that I did a moment on the board. The formula for that is that the moment of inertia of a cylindrical shell is a half times the mass, and then the 2 radii, the inner and the outer radii, added up. Okay, now let's just plug in some numbers here. So a half, and the spokes have a mass of 0.2 m. So the mass of this thing is not actually going to be m, but it will just be 0.8 m, and then ri squared plus r naught squared. This here will be a half times 0.m. Now Ri was 0.8 R2, say 0.8 R0, sorry, plus R0 squared, such as this. Okay, let's just evaluate this with a bit of algebra. So we're going to get 0.4 m, and we can take a factor of R0 squared, and then we're going to have 1 plus 0.8 squared. This here will just give me 0.656 m R0 squared. We're not quite done yet, we just need to add the moments of inertia, and this here will just give me 0.698 m R0 squared. Let's call it 0.7 m R0 squared. We're also going to apply Newton's second law of motion in the rotational world for the first part that we looked at on this problem, in which we had to consider the forces on each of the components. We've already done this for the frame. We're going to do this for one of the cylinders for practice. Up next, let's draw a free body diagram with all the forces on those cylinders. We're going to start off with the rear cylinder. So we're going to have quite a few forces that act. Let's start off with the obvious one. We are going to have some gravity, which is going to be acting straight down, and that's just going to be equal to m2g. We'll also have the normal reaction, which is going to be acting at 90 degrees to the actual surface, and because this is acting on cylinder 2, I'm just going to call this N2. Now, this cylinder was acting with an upwards force on the frame. It was basically supporting it. So by Newton's third law, it will also experience a force in the other direction. All of those should be acting on the same point, by the way, but just a little bit trickier with a digital tablet. So it's going to experience a force in the other direction, and this force will be from object 1 onto object 2. Should we just call this 2N21? That will do. We're also going to have a frictional force, and that frictional force will be acting opposite to the direction of motion right over here at the contact patch. I'm just going to draw this one with a different color because otherwise it can get a little bit too clunky. Okay, so this here is just the frictional force acting on wheel 2. We can just call that F2. There's going to be yet another source of friction at the attachment point. Those diagrams, those free body diagrams in the International Physics Olympiad are pretty tricky, and this is going to be acting this way. Okay, so let's say that this is from the frame onto wheel number 2. Applying Newton's second law, let's start off with the direction which is parallel to the slope. What we're going to get is mg sine of the angle, and then in the same direction we have f21, then take away f2, and this will be equal to the mass times the acceleration along the slope. Now in the perpendicular, the direction of the slope, we're going to have n2, not n, let's call it n, n2, and then take away n21, the other force from the frame, that is, and then mg is also pointing downwards. Now there's no movement in the perpendicular direction, so all of these forces are going to have to sum up to 0. There's another condition that I'm going to write, and that is that this F2 force will actually create a torque, and assuming that we have rolling without slipping, F2 then multiplied by the radius R0 by Newton's second law in the rotational world will give me a will be equal to the moment of inertia multiplied by the angular acceleration alpha.
And this is generally the condition. We can express this in a couple of different ways. So we can say that F2 will have to be equal to the moment of inertia multiplied by alpha, and then divide that by R naught. There's a little trick here that the mark scheme actually gives that I wanted to show you, because alpha, the angular acceleration, is just omega over t, and omega is just v over r naught. We can also say that this is equal to I v over r naught t, and then a factor of r naught. So they've taken this to be I times the linear acceleration, divide that by r naught squared, and that's just an alternative expression which is completely equivalent to this one here.
We've barely scratched the surface with this really long video. There's so many problems that can potentially appear, and this is precisely why you should absolutely do this rotational dynamics physics problem that will help you apply everything that we've learned in a single problem. Have a look over here.